Okay, stats. We're back here again talking about the t-test. I wanted this video to primarily be about confidence interval, but there's two slides I want to finish up about the t-test. These are similar to what we've already talked about. Okay, so this first slide is just showing factors that can influence the t statistic. Okay, one is n and the second one is variance. When we increase the number of people, or our n, what happens is that if I scroll up on this PDF, you can see within the formula. If we increase n, our estimated standard error will go down. Estimated standard error goes down, the t statistic is going to get, excuse me, the t-test is going to get larger. If that gets larger, it's more likely our result will be significant, that we will reject the null. Okay, so as n goes up, we're more likely to reject the null. Sample variance has the opposite effect. Okay? If sample variance goes up, okay, variance goes up here, that means that the estimated standard error is also going to go up. If that goes up, the t statistic is going to go down. We are less likely to obtain a significant result. Okay? And the next slide was just recapping the effect size. Works the same way as before. Only difference, same way we were talking about the estimated standard error. We're now using sample standard deviation, or S, down here to calculate the Cohen's d, and this time we call it estimated Cohen's d. So you see that shift from standard deviation to sample standard deviation makes it estimated, same way we had estimated standard error over here. Yeah. Okay. Bulk of this video, I want to talk about confidence interval. Okay? Confidence interval is basically a way of saying I have a sample mean, but I don't know the population mean. But I can estimate within a degree of certainty where it might fall if the null is true, or if the null is not true. Okay? So it looks sort of like this. Okay? Within this confidence interval, it ranges from 8 to 12, and it is symmetrical, so the sample mean is 10, and it's anything outside of 8 and 12 is going to be significantly different from a sample mean of 10. This means that if we have a population mean of 13, we're comparing it to a sample mean of 10, that these are going to be significantly different. Okay? We'll play this out now with an example. So let's say we do a study to see if glasses influence vision. So we're doing two-tailed at this point. We have 24 people wear glasses, and then we test their vision. We have a mean score of 15 on some vision tests. I'm making up these numbers. And we have an estimated standard error of 1.2. Okay. To do a confidence interval, let me scroll down over here. The formula we're going to use is up here in the top right. We are solving for the population mean using the sample mean, the t-critical, and the estimated standard error. Okay, so the first thing we need to do is figure out what is our alpha level. In this case, we're going to use a 95% or an alpha of 0.05. And we go to our t-table. We use n to figure out our df. So we have a df of 23. It's a two-tailed design. Our t-critical is 2.069. We go to the next slide, it's the same thing, we're just going a bit further. Again, same formula, we're solving for the population mean using sample mean plus or minus the product of the t-critical and the estimated standard error. So what we have is a sample mean of 15 on that vision test, plus or minus the t-critical times the estimated standard error. So we multiply these together, and then we add and subtract that from 15. So it's 15 plus or minus 2.5 gives us a 95% confidence interval of 12.52 to 17.48. Okay? So what this means is that we're 95% confident that the population mean falls between those values if the null is true. Okay? If the null is not true, then the population mean is going to be outside of that. Okay? Let me keep going so I can get to an example and we can sort of recap this. So we're getting a range of two values and a confidence that our population mean is going to fall between that range. And this is great for allowing us to estimate what is the range of our mean. What's that distribution of possible sample means? And then at what point does it become significantly different, right? We can apply this to polls. At what point is it significantly more likely that this candidate wins? And what is that plus minus? What I've done down here is two examples. So in this first one, I've just pulled out the important information. Let's say we have something where sample mean is 67, estimated standard error is 4.2, n is 12, and it's a two-tailed design with alpha this time of 0.1. So we're doing a 90% confidence interval. Okay? So if you look over to the right, pulled out the same information, sample mean 67, estimated standard error 4.2, n is 12, df is 11. I again start by finding my t critical. 1.796 is going to be that t critical. Okay, if I go to my t table, that's where I'm going to find it. Plug it into the formula. Sample mean of 67 plus or minus the product of 1.796 times 4.2. So that's 67 plus or minus 7.54. Then I do that math. 95% confidence interval, that's what CI stands for. It's 59.5 to 74.5. Okay. Let's keep this going. Let's do another example. And this time we have sample mean of 112, estimated standard error of 6.8, n is 43. Two-tailed alpha this time of 0.01. Okay. Just copy the same information over. df is 42. When we find our t critical, we are going to use 40. So our t critical is going to be 2.704. Same steps, sample mean of 112, plus or minus 2.704 times 6.8 leads us to 112 plus or minus 18.4. Then I do the math. Okay. On the bottom end, 93.6. On the top end, 130.4. Okay. We're 99% confident that if the null is true, it's between these two values. Again, instead of going from here's our population mean, we're sort of doing it in an opposite way. Now, the confidence interval is a neat way to approach t-tests from a different kind of perspective. Okay? So we can compare values that we would have compared with a t-test the same way. So we can ask questions like, would a population mean of 90 be significantly different? We can test it using the t-test. We do 112, our sample mean, minus 90, our population mean, over same estimated standard error, we get 3.24. 3.24 is beyond that t critical if we're thinking back to the t-test of 2.7. And so it looks like this, that 90 is in that shaded area, that reject region. So if we were comparing using this confidence interval, a sample mean of 112 to a population mean of 90, this would be significantly different. Okay? Again, 90 is outside of that confidence interval. It's outside of it, significantly different. Now, for the second one, it's what if we use 95, a value that is between the confidence interval? We do 112 minus 95 over 6.8 gives us 2.5. 2.5 less than that t critical of 2.704. So 95 is in this area. Same logic as before. It's not in the critical region. It's in the fail to reject region. So 95 is not significantly different than 112, keeping these other things constant. So to sort of recap this process, the confidence interval is another way to approach the t-test. The population mean is within the confidence interval. It's not in the critical region. So 95 is within the confidence interval. It's not in the critical region, and we fail to reject. The population mean, the hypothetical one we would use is 90. If it's outside of the confidence interval, then we are going to reject that population mean is different than the sample mean. 90 is different than the sample mean of 112. Okay. Hopefully that helps clarify. Let me know if you have any further questions.